Benoît is a professor of theoretical chemistry at the University of Namur. His research interests include the elaboration and application of theoretical chemistry methods in the fields of linear, nonlinear optics, polymer quantum chemistry, vibrational spectroscopies, as well as material sciences. Recent achievements have targeted the second, third, and order nonlinear optical responses of molecular switches, chiral systems, di-radical compounds, fluorescent proteins, air-liquid interfaces, and molecular crystals. Optical phenomena such as thermochromism and thermally activated late fluorescence, and electrochemical processes at electrodes. Recently, he initiated a new direction of his research aiming at predicting reaction mechanism and their thermodynamics and kinetics, exemplary cycloadditions, frustrated Lewis pairs, and doped amorphous silica. Some of these studies have now bridged the gap between materials science and life sciences. Many of these investigations are carried out within an interdisciplinary environment where the theoretical work is intertwined with synthesis, experimental spectroscopic characterizations. He is involved in the management of HPC resources of the University of Namur and in the Federation Wallonie-Bruxelles. Since September 2025, he is a vice rector for research at the University of Namur. Benoît, the screen is yours.
I am very grateful to you for the invitation to give this lecture. It's a pleasure, in a sense, to be here online. And as you have seen, it will be about nonlinear optical responses. That's one side. And the other side, I would like to discuss different methods of calculations applied to molecular crystals. Okay, so let's give the context. If you consider a molecule and you apply an external electric field, like make it simple by considering it is E, the application of this electric field induces some charge reorganization because matter is made of electrons and nuclei. And this charge reorganization can be described by, for instance, the change in electric dipole moment. And you see in this expression, do you see the arrow? No, you don't see the arrow. Do you see the arrow, Paulina? Yes?
Yes, it's very little, but we do see it.
Okay. You have a term which is linear in the external field, and the proportionality is given by alpha, the polarizability. Then you have nonlinear terms, beta and gamma, the first and the second hyperpolarizabilities. This is the way you describe these first and second order nonlinear effects in the case of a molecule. You have a similar equation in the case of macroscopic systems, so like a crystal. But instead of the dipole moment, you have the polarization, which is the dipole moment per volume. And instead of alpha, you have chi1, the linear susceptibility. And instead of beta and gamma, you have chi2 and chi3, the second and the third order nonlinear optical susceptibilities. As you have seen, beta and chi2 are written in red because these are the targets of this presentation. When I write this, I forget about many different aspects. So what I should keep in mind by discussing this is that the dipole moment is a vector, the electric field is a vector, alpha, beta, and gamma are tensors. Alpha is a tensor of rank 2, beta is a tensor of rank 3. So this increases a little bit the complexity of these quantities. But then also, I should consider that the electric field could be static or dynamic. And here you have a general expression for an induced dipole moment created by electric fields oscillating at pulsation omega 1 for the linear term, and omega 1 and omega 2 for the first nonlinear term. And you see that there is a specific notation in the case of beta. You have minus omega sigma on the left-hand side, and you have omega 1 and omega 2 on the right-hand side. Omega 1 and omega 2 are the pulsations of the incident light. So you have two incident lights at these two pulsations. And what you generate is light at pulsation omega sigma, which is equal omega 1 plus omega 2. Of course, you could have different types of combination of these omega 1 and omega 2. The most general one is when there is no relationship between omega 1 and omega 2. And then you are dealing with a phenomenon which is called the sum frequency generation. If the two frequencies are identical, you have second harmonic generation. And again, this will be the focus of this presentation. Other phenomena are the Pockels effect. So you have a change of refractive index when you have an external electric field which is static, and then you have also optical rectification. So what I should mention when speaking about second harmonic generation is that in practice, you have a beam with photons of energy h bar omega, and pairs of photons of energy h bar omega are combined to form photons of twice this energy, so 2 h bar omega. So you do not have any creation of energy, of course. Why is it so interesting, these second order nonlinear effects, and in particular second harmonic generation? Simply because you can tune the laser wavelengths. Here you have on the left-hand side a picture where the incident light is red, 700 nanometers, and what you generate is light at 350 nanometers. So you have divided the wavelengths by a factor of 2. It corresponds to doubling the frequency. And this is exactly what you have in a green laser pointer. You have initially a light at 1.06 micrometer, and you generate light at 532 nanometer, which is typical green. Materials with beta or Chi2 responses, or molecules with beta responses, they could be used in optical telecommunications and signal processing. And one issue that I would like to raise in this presentation is that you can use the beta or the Chi2 response as an indicator of the status of a system, in a sense that it contains a lot of information on the structure, the electronic properties of a system. So if you move from a normal to a cancer ovarian stroma, you would have, for instance, a reorganization of your collagen. And because collagen presents a beta or Chi2 response, and because collagen is different in the two cases, you can evidence the change in structure by using second harmonic imaging microscopy, thanks to that. And one of the key issues with beta and Chi2 is that it disappears for a central symmetric system. So you have a strong relationship with central or non-central symmetry, much more than what you could have with the linear response associated with alpha, or even larger than with the second hyperpolarizability gamma. So this is for the context. I started to work in that field about 30 years ago. And I started thanks to these two gentlemen, late Professor David Bishop and Professor Bernie Kurtman. And these quantities, beta and Chi2, at least for a quantum chemist, they are interesting because they are challenging to calculate and to interpret. And you could tackle many different aspects, from electron correlation effects. I will come back to this in this presentation. In particular, when using density functional theory, you have frequency dispersion issues. You have a strong variation of the response when you get close to resonance. Of course, the these responses are dynamical. So if you have a polymer changing shape as a function of time, you will see variations of this beta response. Additional aspects are electronic versus vibrational contribution. And the topic of today, the effect of the environment. I could have discussed with you about the effect of a solvent on beta response, but here I will discuss about solid state effect and how to describe these solid state effects in the case of Chi2. There are many different methods to calculate Chi2. And about 20-25 years ago, making a stay in Ottawa, we reviewed that with David Bishop. And starting from the easiest, from my point of view, the easiest method, you have the oriented gas model. In fact, nothing is a gas. You are dealing with Chi2 response of a solid. What you do is a simple tensor sum. So you sum the beta tensor of the different constituents of matter, and you make a correction by using typically a Lorentz local field factor. First application by Kemla and co-workers in 75. In fact, they were not calculating Chi2 from beta. In that work, they were extracting beta from Chi2 measurements. So just the opposite. And the idea behind was to make comparison between those extracted beta responses and those that could be measured experimentally for molecules in solution. Another type of method, which is much more simple to I would say, conceptually speaking, these methods are called supermolecule or cluster methods. So you consider one molecule, then two molecules, three molecules in 1, 2, and 3 periodicity direction of your crystal. And then you take the limit of the size tending to infinity. Of course, you never reach that infinite size cluster because the calculation would become too much expensive. First application of this by Dirk and co-workers in 86, and it was for a dimer, but people have considered systems with up to, from my memory, about 1,000 molecules. What you could also do is to apply crystal orbital method. So you take into account the periodicity of the system, and you do one of these periodic boundary condition type calculation. I will discuss that a little bit later. And from the band structure, you calculate the necessary properties, and you use perturbation theory to get Chi2. And you see that, in fact, these are the oldest applications from 1971, because strong approximations were used in these crystal orbital calculations. And in between these, the last two methods, you have what I'm used to call multiscale approaches. You do a calculation of the molecular responses at the ab initio level, and then you do that for a molecule, a few molecules, a unit cell, and then on top of this, you use electrostatic interaction schemes in order to account for the effect of the crystal field, the crystal effects. And in a sense, with this method, it's a bit like using the oriented gas model, besides the fact that when you calculate the response of the molecules, you account for the polarization field of the crystal, but at the same time, in that model, you use improved expression to describe local field factors. So this is the frame of the presentation, and you have understood that I'm going to deal with the two methods here at the bottom. Crystal orbital methods. You can base the approach on the work of Kurtman, Gu, and Bishop. Just a few things to mention. You take advantage of the periodicity, so you focus on one unit cell, the reference unit cell, which is interacting with all the unit cells of the system, which is assumed to be infinite. So you need to deal with lattice summations, integration in the first Brillouin zone. You have a lot of numerical tools behind that you should apply very carefully. One main issue is the fact that the dipole moment is unbound from below, and if you would use it in a straightforward way, you would break the periodicity of the crystal, and you won't be able to apply periodic boundary condition method. So you need to rewrite the dipole moment operator, and for completeness, I have given you the expression here, but I'm not going to focus too much on that. Okay, let's go directly to some results obtained with a crystal orbital method. These are quite recent results in the frame of the PhD thesis of François. Going to present it in September in collaboration with Lorenzo Maschio from the Torino group, from the Crystal group. And you see that there are all these systems are reference analog crystals. So they are used as reference when you do measurements of Chi2 responses. You have 3 inorganic crystals, so KDP, ADP, and lithium niobate. You have urea, small organic molecules, and then a prototypical push-pull pi conjugated system with methyl nitroaniline. So when you do these calculations with a crystal, you start from a structure. It could be from X-ray diffraction, from neutron diffraction, and in most of the cases, you need to re-optimize the structure to get the hydrogen atoms correctly positioned. And then in one step, if you have you know which method to use, you calculate the Chi2 response of your system. These are some technical aspects of the calculations. Everything was done with crystal 17 and 23, sometimes local versions. We look at the effect of the atomic basis set, and here are some results with a given functional PB sol. This is for urea, and at the end we were satisfied with this 6311G DP or star atomic basis set. How does it work when you compare to experiments? So the first thing to tell you about experiment is that for these reference systems, you have a lot of results in the literature. So sometimes everybody did agree, or most of the people did agree, that there should be one reference value, like for KDP and ADP. Sometimes you have several results. So in that case, I took a kind of average and a standard deviation. So this is quite simple in the case of the 3 on the top. For lithium niobate, you have 2 dominant components, and for one of the 2, you have quite a large standard deviation. It's due to the fact that it is difficult to build a pure lithium niobate crystals. MNA, you have this value of 300, and you will see that it is a kind of a red wire in this presentation. Calculations, what I want to show you here are straightforward results with one exchange correlation functional. This is a range separated hybrid. And you see that the results for urea, KDP, ADP, this component of lithium niobate, they are quite in good agreement with experiments. So further on, you can use this method in order to predict the Chi2 response of new systems. For this component of lithium niobate, we are less secure, but there is clearly an issue related with MNA. We are a factor of 3 off, and it's not a question of the purity of the crystal. So anyway, there is a question: is this omega B97X exchange correlation functional appropriate for such calculation? And this is a topic that we address recently and less recently. And I take advantage of this presentation to come back about more than 25 years ago, where we were discussing what should be a good functional to describe nonlinear optical effects. So when you apply an external electric field, it is clear that you have a reorganization of the charges, and you create an induced dipole. And the induced dipole is the source of a counteracting electric field, a field that will counteract the external field. And this is visible when you analyze the exchange potential as calculated with, I would say, a good exchange correlation functional. The straight line here is the external potential, and the curvy line here with some wavy line there. So you see that it has the opposite direction to the external field. So this is the counteracting term. So you can obtain this wavy line by making the difference between the full exchange potential and its all contribution. So the difference between these two sets of oscillations corresponds exactly to this wavy line. That's what you should get. But this does not exist when you use local density approximation or generalized gradient approximation. To get this, you need typically Hartree-Fock exchange. And you have it here in this table. It's alpha and gamma. It's not beta, because at that time it was difficult to do these Krieger-Lee-Jafreti calculations. You see that if you consider MP4 as the reference, with LDA, you have huge overestimations. As soon as you use KLI, you correct for most of this impact. So this was for hydrogen chains. If you use it for a push-pull pi conjugated system and from the same family as methyl nitroaniline, you see what you could get. So SVWN, so this is LDA. B-TRILIP, you have 20% of Hartree-Fock exchange. You see that the behavior as a function of the size of the system for push-pull pi conjugated system is quite different. And in addition, the values that you get here in red and in blue are about 10 times larger than at the Hartree-Fock or MP2 level. MP2 and Hartree-Fock results have been multiplied by 10, as you could see on this figure. And the good behavior should be a bell-shaped curve. You have different solutions. You can use optimized effective potential, but then you reproduce what you wanted to optimize. In a sense, if you want to reproduce the exact exchange from Hartree-Fock, you will reproduce, if you use a correct basis set, you will reproduce the Hartree-Fock result. And that would be the only case where you can do calculation at quite high speed. If you want to reproduce MP2 potential, you lose the advantage of using DFT. An alternative is to use range separated hybrids or long range corrected hybrids. So you cut the electron-electron interaction terms of exchange into two parts, one for short range, and you combine it with DFT exchange, and one with long range that you associate with Hartree-Fock exchange. As soon as you follow this rule, you improve the results. So these are results from Hideo Sekino and co-workers. With the LC BOP here, you are quite close to CCSD. But yet when you have this, you should think at what should be the value of alpha and beta, and what should be the value of mu. So I should speak a little bit about that. Alpha and beta, when you sum this, it corresponds to the amount of Hartree-Fock exchange when the inter-electronic distance is infinite. So it's in the infinite limit, but it could go more or less fast to attain this value as a function of mu, because the larger is mu, the larger you reach, in fact, this asymptotic limit. On the other hand, 1 minus alpha minus beta corresponds to the percentage of DFT exchange at long range. And then if you use a functional like CAM-B-TRILIP, the values would be 35 and 65%. So the question is always which values for alpha, beta, and mu, and this is for exchange. So what about correlation? You can tune the mu value, and that has been proposed by Lior Kronik and co-workers. You can tune mu in such a way that you reproduce Kopman theorems for the first ionization energy. And if you do that, as it is shown on this picture, these are the OT-BNL stars. You see that you have a good agreement for epsilon minus epsilon HOMO and the experimental ionization energy, and you have also very good estimates for excitation energies. So this has been applied, and when you apply this, you end up with an easy conclusion, in a sense that you improve the results without tuning mu, but not that much. And in fact, you do not need to use these range-separated hybrids because you can also use an hybrid exchange correlation functional like M062X, and it would be of the same quality. In other cases, from other works, it has been shown that this is not the universal panacea, and you have limitations. Anna, I have an issue. I have no clock on my screen, and I have, oh yes, I find a clock. I am speaking since how much time? 20 minutes?
Yes, more or less. Do you hear me?
Yes.
Yeah, more or less 20 minutes. So you are on the safe side. No worries.
Very, very good. But there is one more solution, and this is the last one that we have tested during the PhD thesis of François. Why do you need this R-3-Fock exchange? So you should simply think that you have Coulomb interactions. You have Coulomb interaction 1 over R, and at long range you should cancel, thanks to exchange. You should cancel this 1 over R term. So you should have an exchange which is behaving like -1 over R. That is correct if you work in gas phase. If you are not in a material. In a material, the Coulomb interaction is screened, and the screening is associated with the dielectric permittivity. So the refractive index. So in a sense, at long range, the percentage of R-3-Fock exchange should be 1 divided by epsilon R. So if epsilon R is 2, it should be 50%. If it is 4, it should be 25%. So it means that this is interesting. So this alpha plus beta I was mentioning before, their sum should be equal to 1 divided by epsilon R, and like with LC blip, alpha is 0, so beta should be equal to 1 divided by epsilon R. But epsilon R is 1 plus the linear susceptibility. So you could try to find a self-consistent relationship. So the value that you use for your beta parameter in your range-separated hybrid should be the one reproducing the dielectric constant, should be reproducing the linear susceptibility. And this is what we have been doing. So in these 2 figures, you could look at the left or the right-hand side. This is for urea. Urea, you have 3 diagonal tensor components, but 2 are identical. So let's consider XX and YY. And you have here the evolution of chi1 as a function of the percentage of R-3-Fock exchange. So if you take the red curve here, you see that the larger is the percentage of R-3-Fock exchange, the smaller is the linear susceptibility. So this is something that is common. And if you consider smaller and smaller omega L, so smaller and smaller range-separated parameter, mu, you see that you have a decrease. So you have smaller variation. This is also what is expected because the evolution of your percentage of artifact exchange with the interelectronic distance is slower. That's one thing. The second thing that has been plotted here is this relationship. So it is there, 1 divided by CLR minus 1. So this is the self-consistency relationship. So it's quite vertical. And what you see is that you have the best results. So those percentage of artifact exchange reproducing the Chi1 response are those on this line here, because the line is almost vertical. We can say that it is about 50%. If you consider the ZZ component, it's closer to 40%. And if you go from one of these crystals to another one, you can move from about 50 to about 20% in the case of lithium niobate. So in a sense, with this approach, with this self-consistent scheme, you can say that the percentage of artifact exchange at long range now is fixed, but still you can tune your result as a function of the speed to which you attain this value. So what we did was starting from this and calculating Chi2. So this is the same as before, and this is Chi2. And the squares and the dots that you see here, they correspond to the self-consistent percentage that I've shown you before. So you see that this is for the square XX or YY, and this is for ZZ. And so the question is, are these values better or worse than what has been obtained before with omega B97X? So omega B97X, you are here, 100%, 0.30 for mu or for omega, and 2.1 was the response. With the new scheme, okay, this is the self-consistent LC blip. These are the percentages of artifact exchange. These are the two limiting values for omega L, 0.1 or 0.5. And you see that you have Chi1 responses, which are a little, Chi2 responses, which are a little bit larger than the experimental value, whereas with the other functionals, without any tuning, we were a bit lower. And of course, I won't never recommend blip, but this is for comparison. So at the end of the day, there is no obvious improvement when using these optimally tuned screen range separated hybrids. And if you want to come back to the slide I've shown you before, in fact, for urea and many other systems like ADP, KDP, and lithium niobate, we did the same study, and we didn't find any improvement, but the values were already quite good. So what about MNA, for which there was an error by a factor of 3? And in fact, the error was getting worse. So you have here in black, this is the line at the very bottom. This is what we obtained before. We were at, this was this point, 100% of artifact exchange. So if you start from that one, and if you change the percentage, and if you try to see what you could get with a good match for the reproducing Chi1, you get worse, and you get even worse when you use a smaller and smaller range separated parameters. So this was the end of the story in the case of these crystal orbital approaches. And for us, it was clear that the issue due to exchange, in a sense, has been solved as much as it could. Now it is important to do the same with the correlation. It should be non-local. There have been some work in the University of Erlangen on this, but of course the cost effectiveness of the DFT approach is completely lost, and at the moment it has never been used to systems as complex as M&A crystal. So now I would like to discuss the alternative approaches, so the so-called multiscale approaches. And why could multiscale approaches be interesting? And it is simple. You return to one of the papers by David Buckingham, saying that you have, of course, to consider intra and intermolecular effects. For the intramolecular effects, electron correlation is very important. But for intermolecular effects, you could consider electrostatic, induction, dispersion, exchange, overlap. For the kinds of systems that we are dealing with, they are easier to describe, and you will see it. Now, in a sense, in terms of the chronology, I am getting 10-15 years back. And I will show you what is this two-step approach that has been worked out in collaboration with many people from Krakow, Jagiellonian University in Krakow, and in particular within the frame of the PhD thesis of Tomasz Zeigler. So the first thing was to calculate the responses, the alpha and beta responses of the molecules or the ions in a crystal. So just to consider the polarization due to the crystal. So you have here methyl nitroaniline, you have a sphere, and you can tune the radius of the sphere in order to see the field at the center is evolving, or you can look also at the different properties. And we ended up with a statement that with 100 to 200 angstrom radius, it is good enough. Selection of the type of charge is not that much important. We look at many different charges, and in many of the results I am showing you, this has been done with Mulliken charges, but we use also RESP charges and other ones. We check that, and to do that, we look at the potential, the electrostatic potential for an M&A molecule. So this has been calculating on the right-hand side. This is what you get by using the point charges. So you have negative and positive electrostatic potential. And on the left-hand side, this is the result of two calculations, one calculation with crystal and one calculation on a single molecule. And what is represented here is the difference. And if you look at the two pictures, you see that the zone with negative and positive are more or less at the same place with the same shape. But this is not the only proof of the quality of the approach. So with this first step, you know what are the alpha and the beta response of a molecule in its crystal environment. What you need to calculate from this is the Chi2 response. And to get the Chi2 response, you need to evaluate the D matrix. And the D matrix is the one relating the external electric field E to the local electric field. You need the same D matrix to go from alpha to Chi1. That has been done for Chi1. That has been done for Chi2. From Chi1, of course, you can get epsilon and the refractive index. And what is important to consider is that you have an expression for the D matrix elements, and you get it by making a summation over all the molecules of all the unit cell of your crystal. So it is a bit the same like with periodic boundary condition approaches, because you need to make this lattice summation, and this is performed by using the Ewald method. What I want to show you briefly is that this method to calculate its kind of local field correction is not new. You can come back to the work of Silberstein in 1917. If you have two atoms in a molecule, you have the field here. You create an induced dipole on A and an induced dipole on B, And in fact, the induced dipole on B is creating an additional field in the same direction as the external field on A. So at the end of the day, when you look at the response in this direction, in the direction of the AB bond, the polarizability is larger than the sum of the polarizabilities of A and B. This is this expression here. If you look at the application of an external electric field in the opposite direction, in the perpendicular direction, the induced dipoles, they create a field which is counteracting the external field. So the total polarizability in that direction is smaller than the sum of the polarizabilities of the constitutive atoms. And this is a simple representation of this effect. And in fact, this is what is done when you consider this summation here, but you do not have two atoms. You have several molecules in the unit cell, and you have an infinite number of unit cells as in a crystal. This technique has been used to calculate polarizabilities of molecules from polarizabilities of atoms. It has been used to calculate polarizabilities of clusters from polarizabilities of molecules, and also by Mun and also Dijkstra to calculate beta and gamma, and then Chi2 and Chi3. A few applications now. From MNA to NLO organic crystal. So this is the unit cell of MNA. If you want to look at the beta response of the isolated molecule and compare it with the beta molecule of the molecule in the surrounding point charges, you have an increase by about 80%, as you can see here. And now some results of Chi1 and Chi2. So if you take Chi1 with the charge field, so the one that is considered here with the point charges, you see that your Chi1 response is in quite good agreement with experiment. It is less good if you if you neglect these external point charges. And it is the same in the case of Chi2. You have a response here which is about 300. We did a lot of calculation. We check also the performance of different exchange correlation functional. We look at the vibrational contributions. We find at the end of the day that it is feasible to calculate the NLO responses of the molecules at a high level, like CCSD. It's also possible to do this with some specific exchange correlation functionals, and the scheme is working pretty well. You have some information about these methods for molecular crystal and also for ionic organic crystal in these two papers. And this is the work of Tomáš, and the supervisor of Tomáš was Katarzyna Stasnicka, also from Jagiellonian University in Krakow. You apply the method to this set of systems. And here are some quick demonstration of the performance of the scheme. You have the calculated Chi2, you have the experimental Chi2 for these systems, and you see that if you do the beta calculation with MP2, it is not that bad. The slope here is close to 1, but you can also use DFT. The slope is less good, but still you have a predictive character. You can do the same for the refractive indices. It's working quite well. So at the end of the day, when you see this, you end up with an easy conclusion. It is not necessary to do crystal orbital calculations. You can use this two-step approach. The difficulty with this two-step approach is that you need to build all the steps, and you can also make it more or less automatic, but still, if you do MP2 calculations, you need to be careful when you account for the frequency dispersion. Then I have some slides with a work that was done with Anna. Anna came with one of his baby, the QTAIM, Quantum Theory of Atoms in Molecules. And the point was to improve the calculation of the local field, because there are many things that I didn't tell you. And one of the things that I didn't tell is about the way we calculate these local field correction. So when you do the summation here, what you can do is you can assume that to do that, the total polarizability of the molecule is positioned at its center of mass. But if you do that, it's a very poor result. It's like a dipole approximation to look at interaction energies. But what you can also do is to distribute this polarizability. And at the beginning, the polarizability was distributed equally on the different non-hydrogen atoms. And in the case of MNA, in the case of all these systems, it's working pretty well because you have one major direction of polarization and one major direction of hyperpolarization. When your molecule is getting more complex, you might need to use an improved distribution of the polarizability. And you can use this QTIM scheme, and especially this formulation where the quantities are origin independent. I have an application of this in the case of MNA. In the case of MNA, it was not necessary, so I can just tell you that it didn't change much. Of course, you move from 363 to 306, but the differences are within the experimental standard deviation. So this was for Chi2, and it's the same for Chi1. But it's much more interesting for this molecule. It's alpha-methyl benzylamino nitropyridine. And you see that you have two parts in this molecule. So you have this part here contributing to the polarizability, and this part here contributing to the polarizability and to the first hyperpolarizability. So when you distribute alpha in an equipartitioning way, like here, you get typically refractive indices which are overestimated with respect to experiment. As soon as you use the QTIM partitioning, your results are much better. You get closer to the experimental value. And from this, with Anna, we have been able to analyze and to compare several of these compounds with chemical variations, and it was possible to show how the Chi2 response was appearing as a function of the modification of the chemical structure. I'm getting very near the end, probably 2 minutes. Thanks to these methods, and this was not my purpose when preparing this presentation. Thanks to this method, you can do some chemistry. So we've been working with people at Chi11. They were working on a metal organic framework, in particular MIL53. They had an aniline motif, and they wanted to improve the Chi2 response. So they built a system with paranitroaniline linkers, but the results were very strange. And we spent a couple of years with Thomas to try understanding what was going on. But we were applying this method, and this method, this multi-scale approach, can be used for any system. So the take-home message is the following: there is a method available to calculate Chi2 of molecular crystals, and this is multi-scale scheme. It is not conceptually the simplest, but it's working, and I think it contains the right physics. But if you are a theoretician, you sometimes like to find other schemes like these periodic boundary condition methods. And today I want to conclude this talk by saying that it doesn't work. It works for some systems, but there are still some need of improvement. I want to thank all the people you have seen the pictures, because they are great collaborators. I want to thank these funding agencies. I want also to thank you for your kind attention. And I want to thank Eric Magadams for these pictures that she has drawn during an SAS meeting in San Francisco. So thank you very much, and I welcome your questions.
Thank you, Benoît, for a very interesting lecture. It's nice to see that that you have developed a method which is working for organic crystals, even if it's not fully periodic approach. Or thanks to not using fully periodic approach, actually. We are waiting now for the questions. We do have some. Thank you very much for presentation from Alessandro Dolmella. And we have a first question from Shabam Som. These Q-tame calculations can be used to determine the H interactions. Is it valid or not?
You speak about hydrogen bonds?
Hydrogen to hydrogen interactions.
This is far from my field of expertise. For me, the QTIM approach that we have been using here was simply used to distribute the polarizability. So we started from a distribution of the dipole moment into different terms. So you see here on the screen, so you have a sum. So this is for each atom of your molecule. And what was done was a electric field derivative of this mu in order to get the polarizability tensor. So I am not sure that QTIM should be blamed or not to calculate HH interactions. I think that this aspect should be embedded into the level of approximation you employ in order to make your quantum chemistry calculation. So I have no idea whether this is sufficient with DFT, but what I want to say is that HH interactions are probably not that much important when you want to calculate a first hyperpolarizability and therefore a Chi2 response.
While we're waiting for another questions, I have a very practical question. So you have shown us results over the years, and I guess you are still using this new, developed method nowadays. How long does it take, or maybe firstly, you probably need to use HPC systems, not a single computer laptop.
Okay.
And how long it takes for regular kind of organic molecule?
Okay. If you want to calculate the beta responses at a high level, so the first step of the multi-scale approach, it would take, let's say, maybe 1 week of CPU time if you want to do the calculation nowadays at a CCSD level if you are using a hundred of processors, hundreds of cores. Mm-hmm. The calculation of the local field corrections is nothing. It's just a few minutes. That's for the multi-scale approach. But you have many steps to build your data file and to analyze your results to go from one step to the next. When you do a crystal orbital calculation, and if it is a calculation of on urea, you might need more or less the same amount of time for a single calculation, but it is DFT. If you want to do calculation on MNA with 128 cores, these days it takes a few weeks of CPU. It is much more. And I am not explicit enough when I answer this question. Everything is related to this slide here. If you do the calculation with LDA or GGA, it goes fast because mm-hmm. the lattice summations, they converge very rapidly. So you do not need to go far in these lattice summations. The integration in the first Brillouin zone are also fast. So it won't be expensive, but at the same time, it won't be accurate. As soon as you have R3-fork exchange is converging very slowly, and the convergence is getting slower and slower, when the band gap of your system is getting smaller and smaller as well. And that's why you need to push the lattice summation very far, and this is why you have very big values here. It means that you use in some of the summation 36 unit cells.
Okay.
And you have to do this for all direction. So that's why for the best calculation, like those performed with Omega B97X, where you have 100% of R3-fork exchange at long range, this is why it takes weeks of CPU time. But from the point of view of, I would say the ease of calculation, it's easy. You have a structure, you put it in the crystal code, and if you know which basis set and which functional to use and which parameters to employ, it is straightforward. You make everything in one step. But it is expensive.
So I guess it's why Anna is doing her a database approach.
Of course, this is also possible.
We have another question from Martin Breza. Nitro compounds such as MNA cause problems by NMR calculations as well. It is usually explained by omitting the small component of the relativistic wave function. Yeah. So do you use any relativistic corrections?
No, not at all. And I am not expecting any role of relativistic effect for these for the system I've presented you here. We didn't do works in that direction, but there are several studies by Patrick Norman. And with some of these systems, you would have variations of less than 1%, not even 1%.
Mm-hmm.
I am not saying anything about lithium niobate because I don't know niobium enough. But the question was about MNA, so it's
yeah, organic systems. Mm-hmm. There's a thank you from Sabam Sam for the answer.
Okay, thank you.
If I may, just a small question.
Yeah.
So Benoît, do you think it would be easier if you switch to inorganic compounds? Like, hardcore inorganic for NLO properties?
By using the multiscale approach?
Yes.
We know that the technique is working for these systems like the metal organic frameworks. We know also that it is working with these ion pairs, so for these ionic organic crystals. Then for fully inorganic crystals, I think that it would deserve to be tested, but definitely I would go using QTIM. That's one thing, and we know also from the work with Thomas that when there are anions and cations, we should be careful when calculating the dressed polarizabilities and hyperpolarizabilities. And if you have noticed, this is why here in this second paper there was an erratum, and it was not an erratum of 3 lines, it was an erratum of 5 pages.
Oh wow.
Yeah. So there was something substantial that we missed at the first time. Didn't change much some of the results, but we realized there was an issue with these charges. So let's try, Anna. It should be tried.
I mean, it's Organic Chemistry Institute, so why not?
Yeah. It should be tried.
Krzysztof?
Yes, I wonder how much these parameters change as a function of pressure in extreme conditions. Imagine that you apply, I don't know, gigapascal or 10 gigapascal or 100 gigapascal pressure.
There has been some work, but by Roberto Cami from the University of Parma on this. It was mostly for isolated molecule. He has worked a lot also with Roald Hoffmann on that topic. I do not remember on which system he has made some calculations. I do not remember he has been considering, I would say, large organic molecules with large beta responses, but this can be done. And I know that with extremely high pressure, you have variations because you condensate a little bit your electron clouds. But you really need to go to very high pressure. If you want, I can check for the reference, but I do not know by heart what was the amplitude of the effect. But Roberto Cami has done that, and he has done that by using, by the way, by using the PCM scheme, because with polarizable continuum model, you have a cavity which has the shape of the molecule, and he was reducing the radius of that cavity in order to create the pressure on the system. It was a very clever approach.
Yeah, it would be very interesting to see appearance or disappearance, a kind of a phase transition when you apply pressure, for example, and you are going from non-central symmetric system to the symmetric system.
Okay, but that I was not, Christophe, I was not speaking at all about that. I was speaking simply about the fact that the effect, the pressure could be an external parameter tuning the beta response. Of course, you have these other effects on the phase transition.
Thank you.
For that there are other approaches to do that, as far as I remember, like to include the effect of temperature.
Thank you. I do not see more questions.
Yeah.
Let us thank Benoît for this excellent lecture. Thank you.
Thank you very much.